Hi, today we're going to talk about exponential growth and decay. Yesterday, we went over separable differential equation. So we looked at non-separable and we looked at separable, but we mainly worked with separable differential equations. So we're going to utilize a lot of that today in our exponential growth and decay models. Now, you've actually had experience with exponential growth and decay within both Algebra 2 and pre-calculus. You are going to need your calculators today, so make sure you have those handy. Okay. All right, so exponential growth and decay functions are differential equation of the form, so exponential growth and decay functions come from differential equations of the form dy dt equals k times y, where k is a constant. So starting with dy dt equals ky, okay, using what we learned yesterday, if we want to go ahead and solve this equation for y, well, we know we have dy over y is equal k dt, taking the integral of both sides. We end up with natural log absolute value of y is equal kt plus c. I'm going to go ahead and call that c1. Okay. Now if we went ahead and raised both sides to the exponential, then we're left with y is equal to e to the c1 times e to the kt. Well, e to the c1 is still a constant, so we can go ahead and replace that with just plain old c. We have y is equal ce to the kt. Okay, so that is our exponential growth and decay function. Okay, so let's just keep in mind that dy dt equals ky, k times y, is the derivative of y with respect to t is directly proportional to y. And is directly proportional to y by this factor of k. Whereas if you were given the differential equation dy dt is equal k divided by y, this means that the derivative of y with respect to t is inversely proportional to y. Okay, so let's go ahead and take a look at what we have so far. So we have y is equal c e to the kt. Okay. So C is our initial amount Y would represent our new amount. The K represents our constant of proportionality. And of course our T represents our time. Now if K happens to be greater than 0, then that implies that you are going to have exponential growth. Whereas if K is less than 0, then that implies that you will have exponential decay. Okay, let's take a look at an example. So here's example 1. We're going to take a look at an experimental population of fruit flies. So let's say, suppose an experimental population of fruit flies increases according to the law of exponential growth Okay, so we have an experimental population of fruit flies. They are going to increase according to the law of exponential growth. Okay, so here's some information that we have on these fruit flies. Okay, there were 100 fruit flies after the second day, and 300 flies after the fourth day. What I want to know is approximately how many flies were there in the original population. So approximately how many flies were there in the original population? Okay. So this we are going to set up with an exponential growth model. All right. So we're going to start off with our exponential growth formula. Okay, so we're going to start off with y is equal CE to the KT. Okay. Now, C is going to represent the original amount of flies, or the original population of flies. Then we have actually two sets of information. I know that there are 100 flies after the second day, and then there are 400 flies after the fourth day. So we're going to use both of those sets of information in hopes of finding what the original population was. So let's start with the 100. So we have 100 flies is equal CE to the K times 2. Okay. We also know that 300 flies is equal to CE to the K times 4. Okay, now if we were to solve both of these for C, we get 100 divided by e to the 2k is equal C. And over here we get 300 divided by e to the 4k is equal c. So now we're going to deal with that wonderful property we learned back in geometry, the transitive property to cut out the middleman. If this term is equal to c and this term is equal to c, well, if they're both equal to c, then they have to be equal to each other. So we can set them equal to each other. So 100 divided by e to the 2k is equal 300 divided by e to the 4k. So now we have this set up as a proportion. So let's go ahead and cross multiply. 100 e to the 4k equals 300 e to the 2k. So we should be able to solve our constant of proportionality. Okay, so here you can divide by e to the 2k, divide both sides by 100, those reduce to 1. So e to the 4k divided by e to the 2k is just e to the 2k. 300 divided by 100 is 3. So we get e to the 2k is equal to 3. Natural log of e to the 2k is equal natural log of 3. 2k is equal natural log of 3. Or k is equal 1/2 natural log of 3. So now we know our constant of proportionality. It is k is equal to 1/2 natural log of 3. So we should be able to use that to find our initial value, our c. So we know that y is equal to ce to the kt, but k is 1/2 natural log of 3 times t. Okay, well, we can, at this point, we can use either the 100 or the 300 to help us solve c. And it should come out to be the same answer. We use the 100. So after 2 days, when t is equal 2, we know we have 100 flies. So when we set this up, we say 100 is equal c e to the 1/2 natural log of 3 times 2. Well, 2 times 1/2 is just 1, so we get 100 is equal c e to the natural log of 3. Well, e to the natural log of 3 is just 3. So 100 is equal 3c. And solving for c, we end up with c is equal to 100 divided by 3, which is roughly 33.3. So you can't have 33.3 fruit flies on the original. So we'll just call this 33 flies. Okay. So with this particular problem, we had an experimental population of fruit flies. It seems as though our initial population was 33 flies. After day 2, we had 100 flies. After day 4, we had 300 flies. Exponential growth. Okay, now that we know what C is, we know what K is, we could figure out what our population would be after maybe 15 days. You just plug in 15 for T. 33 for C, 1/2 natural log of 3 for K, and then you can find those values. Okay, let's go ahead and try another example. Okay, this one, example 2. Okay, suppose you have 10 grams of plutonium, isotope Pu-239, and it was released in the Chernobyl nuclear accident. Okay, how long will it take for the 10 grams? So how long will it take for the 10 grams of plutonium to decay to 1 gram of plutonium? Okay. Now, the piece of information that they give us here is that the half-life of plutonium, isotope 239, is 24,100 years. Okay. So let's see if we can understand this in perspective. All right. So let's say we start off with 10 grams of plutonium. In 24,100 years, that 10 grams will have dissipated into 5 grams of plutonium. If we go another 24,100 years, that 5 grams will have dropped down to 2.5 grams. So in 48,200 years, the 10 grams of plutonium would decay into 2.5 grams. It would take another 24,100 years for the 2.5 grams of plutonium to decay into 1.25 grams of plutonium, and so forth. So just by those calculations, we should know to go to 1.25, just by doing the math there, that it's going to be 24,100 times 3. So it should be over 72,000 years. So when we do get our answer, we want to compare it just to make sure we're in the ballpark there. So we're going to go ahead and start off again with our exponential growth and decay formula. Y is equal to CE to the KT. Now when you look at this formula, you do see that you have 4 spaces here. Okay, sorry about that. A custodian came in and vacuumed the floor. I can get started back. Alright, so we're going to start off with our exponential growth and decay formula, Y equals CE to the KT. Now, very key word here with the information that's given to us is half-life. So our initial amount of plutonium is 10 grams, so that's our C. What I do know is that in 24,100 years, that 10 grams of plutonium will be cut in half, which means that my new amount is going to be 5 grams. So we get 5 is equal to 10 E to the 24,100 K. Okay, so here we should be able to solve for K. We only have one unknown, so 3 of our spots are filled. We have the one unknown. Divide both sides by 10, so we end up with 1/2 is equal E to the 24,100 K. Natural log of both sides. So we end up with natural log of 1/2 is equal natural log of E to the 24,100 K. So that's natural log of 1/2 is equal to 24,100 K. So K is equal ln of 1/2 divided by 24,100. So that's our K. Okay. So now we can use that to find the time it takes for our plutonium to go from 10 grams to 1 gram. So here Y is equal to 10e to the KT. Well, that's going to be ln of 1/2 divided by 24,100 T. And that is our exponent there. Okay. Now I'm going to rewrite this. So Y is equal 10e. I'm going to write it as T over 24,100 times ln of 1/2. And you'll see why in a minute. Okay. Now here, this e to the, let's see, what did I do? E to the ln, or T over 24,100 times ln of 1/2. Can rewrite that as 10e to the ln of 1/2 raised to the T over 24,100. Remember, a times natural log of b is natural log of b to the a. So we're using the power property of our logs there. Well, e and natural log are inverses, so we're going to end up with y is equal 10 times 1/2 to the T over 24,100. Okay. Well, I want to know what my time is when y is equal to 1. So we get 1 is equal 10 times 1/2 to the T over 24,100. 1 over 10 is equal 1/2 times T to the 1/2 to the T over 24,100. Okay, let's take the natural log of both sides. So we're going to get natural log of 1 over 10 is equal natural log of 1/2 T 24,100. Now, using our power property of logs, we can bring this out front. And what we're going to end up with is ln of 1 over 10 is equal T over 24,100 times ln of 1 over 2. ln 1 over 10 divided by ln 1 over 2 times 24,100 is equal to T. So go ahead and plug those values into your calculator, and you're going to end up with T is equal to 80,000, 58.5 years. Okay, and that's kind of in line with what we were thinking before when we just on the top of our head, we knew that it was going to be over 72,000 years or so to go down to 1.25 grams. So that answer is definitely in the ballpark there. Okay, to finish up, you have a worksheet where you have, I think, 13 or so problems that you need to work out. Please go ahead and do your work on another sheet of paper. You will need to use a calculator for some of your problems. And the last thing I wanted to remind you of is when you're talking about half-life or population doubles or population triples, basically what happens there, you had a problem before where we talked about the half-life of plutonium. Well, your new amount is going to be 1/2 of what your original amount was. So here, because I know that this new amount, y, is going to be half of c, I can write it as such. So this y, I can replace it with 1/2 c is equal ce to the kt. then when you divide both sides by c, you get 1/2 is equal to e to the kt. Okay. What about if your population doubles? So y is equal ce to the kt. If my population doubles after a certain time, then I know that my initial amount, my new amount, is going to be 2 times bigger than the initial amount. So if my initial amount is c, my new amount is going to be 2c. It's equal ce to the kt. Again, dividing both sides by c, we get 2 is equal e to the kt. So that's if it doubles. Okay, and you can go ahead and do the same thing for triples or quadruples. So you may get some problems where they don't give you an initial amount or a new amount, but you're able to work through this and still set up an equation to where you really don't need it. We could have done a half-life problem without writing the 5 and the 10, and if you look back to your notes, you do see you ended up with 1/2 is equal e to the 24,100k, because that was the half-life. Okay, so if it triples, then it'll be 3 is equal to e to the kt. If you had 1/3 the original amount, you'd have 1/3 is equal e to the kt, etc. Okay, all right, I hope this has been beneficial and helpful, and good luck.